Hello, everyone. These are the promised notes on the Fourier series. Sorry that they are a little bit later than planned, but they are coming out now. You had the ones from Matt from last year. There's a couple modifications from those notes if you've already reviewed those, so just keep an eye for those on the printed version. But here is also the recording of me going through those notes. Okay, Fourier series. We will end the course by introducing an interesting topic that will likely come up a lot, especially when studying signal processing or partial differential equations. This is conceptually very similar to the Taylor series. But before we can begin, we are going to pay some old friends the sine and cosine functions a visit. Sine and cosine. So we know both of these are periodic functions, which means after so much time has passed on the x-axis, we're going to repeat values. We're going to have repetition occurring in our functions, right? So a function f is called periodic with period t, where t is greater than 0, as long as if x is in the domain of f, then x plus t is in the domain of f2. And for f at x plus t, its height is equal to the height of just f of x for any x in the domain of f. So for example, if we just draw out one of our functions here that we know is periodic, we'll do the sine function. Well, that is not what I meant. There we go. Okay, then if we choose some point here and look at this analogous point here, we label this x and this x plus t, that we see that this function is repeating after every period, right? The height is the same whenever we add t to whatever, any of our x values, okay? So that's what we mean by periodic functions. A cool fact, suppose that f and g are both periodic functions with a period t, then it is not hard to show that the period, the product of f times g at x is also periodic with that same period t. And any linear combination of c1 times f of x plus c2 times g of x is also periodic with period t. Okay, so if we have two periodic functions with the same period and we multiply them by one another or add them in some linear combination to each other, then that result, product or summation, is itself periodic with the same period t. Okay, so the product or addition of two periodic functions has the same period as those periodic functions, assuming they're the same. All of the basic trig functions are periodic, but they aren't the only periodic functions. Can you think of any others? Let's draw a few out here. So of course, our constant function is also periodic, as for whatever period we choose, it's going to repeat itself, right? It's constant. And we can draw out some other piecewise functions here that would also be periodic. So let's say we had something like this. This would be periodic if we extend in either direction. And so let's draw one more. Some function like this would also be periodic. Right? So it doesn't have to just be sine or cosine function. We can have some sort of piecewise function that's repeating, but all of our trig functions are themselves periodic. Our sine function, f of x equals sine x, is periodic with the period 2 pi. But it is also periodic with the period 4 pi, or 6 pi, or even 496 pi, right? Any even integer times pi is going to be, except for 0. Any even integer greater than 1, or less than -1, any even integer that does not equal 0 times pi would also be a period for the sine function. Of course, we have that any periodic function with period t is also periodic with period kt, where k is a positive integer. Okay? K is a positive integer. Okay, so not negative, right? So positive integer. Okay. The smallest value of t for which f of x plus t equals f of x is called the fundamental period. Okay, so that's our smallest t value that we can find where this property holds. Okay, and for our sine and cosine function, the fundamental period is going to be 2 pi. Okay, so now we understand a bit more about periodic functions and how we can have multiple periods for a function, and the smallest period that we can find is the fundamental period of that function. Back to our basic trig functions. We recall that the transform function f of x equals c sine k times x minus p plus q is periodic with the period of 2 pi by k, right? So that is this value right here that's outside of the bracket that contains x minus whatever our horizontal shift is. Okay? And the same thing goes for the similar cosine function. This fact will come in handy for us in the near future. Suppose that we have the constants m and l such that m is a positive integer and l is greater than 0 is a real number. Show that the function sine m pi x over l and cosine m pi x over l are periodic with the period 2l for any choice of m and l. Okay? Well, let's look at sine first. And let's just rearrange what's inside here to look like this. Okay, and so therefore, this quantity right here, m pi over l, would be our k value from our description of a function up here, not description of a function, from our transform function up here, right? So that is our k. So therefore, this period will equal to 2 pi by k, which is equal to 2 pi over m pi over l, which would equal to 2 pi, I'll cancel out in a minute, times l over m pi. Okay, and so what we end up doing is we seeing that these 2 pi's can cancel out, and so we get equal to 2l over m. Okay, so that's close, right? We have the period 2l, but we know that, m is a positive integer, right? And we know that a positive integer times our fundamental period is also a period, or a positive integer times any of our periods is also a period, right? And so therefore, 2l over m times m is also a period because m is some positive integer. So we'll cancel these out. So therefore, 2l is a period of sine of m pi x over L, right? And the key word is here is a period, right? There are infinitely many periods, right? And if we take any of our periods and multiply it by a positive integer, we get another period, right? Okay, so 2L is a period of sine. It's not necessarily the fundamental period of sine, and sine being sine m pi x over L. Okay, and similarly, we can do a similar analysis to show that cos m pi x over L also has period 2L. Okay, and the question was asking us, we want to show that this has a period of 2L, and we have done this right here. And I'll just refer to previous page. And that is because m is a positive integer. Okay, and that's where we talked right up here, where some positive integer times our period is also a period. Okay, good. Okay, let's introduce another topic that will come in handy. Okay, orthogonal functions. Okay, so the dot product, also called the inner product, can be defined for vectors. To find the dot product of two vectors in Rn, we multiply component-wise and add up the result. For example, if we had these two vectors and we took the dot product of them, then we would be adding together 4 times 1 plus 2 times 2 plus -3 times 3, which would equal to 4 plus 4 minus 9, which is equal to -1. So the dot product of these two vectors would be -1. Okay, so when we talk about dot product of vectors, we multiply component-wise, and that gives us a value. It would now be useful for us to generalize that idea to functions. Given two real valued functions, u at x and v at x, the inner product of u and v on x is an element from a to b, so the closed interval from a to b, is defined by the inner product of u and v is equal to the integral from a to b of u times v with respect to x. Okay, so the integral from a to b of u times v with respect to x. Okay, so we can calculate this integral, and that will tell us the inner product of our two functions, u and v. Okay, two functions, u and v, are said to be orthogonal on the interval x from a to b inclusive if the inner product of u and v is equal to 0. Okay, cool. Okay, so we say they're orthogonal if the inner product equals 0. And now a set of functions is called mutually orthogonal if each distinct pair of functions in the set is orthogonal on x is an element of AB. And let me just reword this one sentence. Each pair of distinct functions in the set. Okay, so that means for every possible pair, if we take one function from the set and another function in the set, those two functions cannot be the same. So two unique functions from that set and their inner product is 0 for every pair, then that whole set is known to be mutually orthogonal. Okay? For example, let's do a simple example. So show that the functions cos x and sin x are orthogonal on the interval x is an element of negative pi to pi. So that means we want to show that the inner product of cos x sine x, which is defined to be the integral from negative pi to pi of cos x sine x dx. Okay? And we want to show that this is 0. If it's 0, then that means cos and sine are orthogonal. Okay? Good. So we'll go ahead and start doing that. What we'll do here is we'll notice we could do this with product rule in reverse, but I'll do this with a u sub. So I'm going to let u equal to sine of x, and that means du by dx is equal to cos of x. And so we can say that du is equal to cos x dx. Okay? So we have that. And this is a definite integral. So because of that, we need to update our bounds. Okay? And so we'll do that. I'll do it in a different color. So we have that u at pi, let's do pi first, pi, which is equal to sine of pi, is equal to 0, and u of negative pi, which is equal to sine of negative pi, is also equal to 0. Okay? And so what we'll actually notice right away here is that when we replace x with u, we are going to get 0 to 0, and this will be u du. Okay? Now, I am going to continue this, but right off the bat, when we see an integral where our bounds are the same, we already know the area under that is going to be 0, right? The area under a function where we don't traverse any of the x-axis, they're right beside each other, right? There's no area under there because there's no width, right? For that rectangle, let's say we're doing like a Riemann sums, right? So that means this is already enough to say that this value will be 0. We already know that the inner product of cos x sine x will be 0. Will be 0 because of what I just said. So this already tells us that this will be 0, but let's just move forward with it anyway. So this would be u squared by 2 evaluated from 0 to 0, which of course, if we did this off to the side, we would get 0 squared by 2 minus 0 squared by 2. That's top minus bottom. And of course, this would equal to 0. Okay? But let's say we did switch back to our original function, then this would be sine squared x by 2. And we'll go back to our original bounds, negative pi to pi. And once again, top minus bottom would be sine squared pi by 2 minus sine squared negative pi by 2, which of course, sine of pi is 0 minus 0 equals 0. Okay? So there's 3 different ways that we can prove that this is 0, and I've shown them all here. Okay? And so therefore, cosine and sine are orthogonal on the interval negative pi to pi. Cosine of x and sine of x are orthogonal on x is an element of negative pi to pi. Okay, I'll put a box around that. Okay, right? And so I just want to do one additional note here. From up here, we talked about a set of functions, right? So a set notation, we would use curly braces. So therefore, the set cos x sine x. A set of functions is called mutually orthogonal if each pair of distinct functions in the set is orthogonal on our interval x is the element of a to b. Okay, so the set cos x sine x is mutually orthogonal on x is an element of negative pi to pi. Okay, so that means if we had the set that contains cos and sine, because the only distinct pair of functions from that, pair of distinct functions from that set is cos and sine, and we've shown that their inner product is equal to 0, that means the overall set is mutually orthogonal on that interval. Okay, because the only pair of distinct functions from that set is sine and cos, and we've just demonstrated that the inner product of cos and sine is equal to 0, and thus they are orthogonal to one another, and the entire set is mutually orthogonal. If we had a larger set, we would have to show more work, right? Okay, I just wanted to add that in to nail home this point right here. Okay, good. Now, in fact, we can go further. Okay, so just some minor modifications to this, this right here, right? Is we're going to change the to any set of two functions comprised of cos and or sine, and we're going to change this m to n and add the restriction that m does not equal n. Okay, so let me now read this through. In fact, we can go much further. Any set of two functions comprised of cos and or sine, cos being, cos at m pi x over L, and or sine at n pi x over L, where m does not equal n, form a mutually orthogonal set of functions on the interval x is an element of negative L to L. Okay, this is because by integration, we can show that. Okay, let's go through a couple integrals. The integral from negative L to L of cos m pi x over L times cos n pi x over L dx will equal to 0 if m does not equal n. There's that restriction we saw up here, right? So that means if we had a set of two cos functions with different m's and n's here, two values that are different, that set would be mutually orthogonal because it equals 0. Okay? Same thing can be shown here, that for if we have the integral from negative L to L of sine m pi x over L times sine n pi x over L dx, once again, if m does not equal n, if they're different, then our inner product will be equal to 0. And so therefore they will be orthogonal to one another. So the set that contains those two sine functions with different m and n will be mutually orthogonal. Okay, and actually our restriction gets a little bit simplified here when we have a sine and a cos, right? So two not being the two sines or two coses. This will be true for all m and n, right? So we don't have that restriction that m does not equal n for when we have a sine and a cos inside our set, right? And so these are just some common things here. These, of course, will be left as a for you to try to solve these, but we can take these at my word for the next few pages, okay? Good. Okay, so just one more time. Any set of two functions comprised of cos and or sine, where m does not equal n, form a mutually orthogonal set of functions on the interval x is an element of negative L to L. This is because by integration, we can show all of these things to be true. For our work before, we can see that negative L to L is a period for each of the trig functions involved, right? From negative L to L. And that's because sine of m, what did I use? I used n up there, n pi x over L, and cos of m pi x over L have a period to L. Okay? So that means our interval that we have from negative L to L encompasses an entire period of those functions. Consequently, integrating any such product of trig functions over their period, this is key, can be done extremely easily. Okay? Now note, we can prove similar results to the first two cases for integrals over the interval 0 to L as well. Something that becomes very important in certain applications. Okay? Good. So evaluate the following integrals without doing much work at all. Okay? I'll show a bit more work for the first one, but in the next ones, the pattern kind of stays the same. So let's say we had sine of 2x times cos of 4x. Okay? Right? If we had sine of 2x, well, that will be equal to sine of m pi, I used n up there, n pi x over L with, okay, well, what would our n need to be? Our n would need to equal to 2, and L will have to equal to pi to cancel out that pi, right? And similarly here, we get cos of 4x equals to cos of m pi x over L with m equaling 4 and L once again equaling pi, right? Okay, so we can see how sine and cos of 2x and 4x respectively came from our formula for sine and cos up here, right? So we've just demonstrated that, and that means these integrals here apply. And so we look, okay, sine and cos, these two values are not equal to one another, okay? But if we look at our integral up here, where we have sine and cos, and remember, we have L and negative L, and L is equal to pi. So that means we have L equals and negative L equals negative pi, right? Okay, so this formula definitely applies. And so therefore, this will equal to 0, regardless of if these coefficients here are equal to one another or not. So this equals 0. Okay, now we have the case where cos 2t, cos 3t. Okay, so that means these two functions once again have different coefficients. Okay, these are not equal. And so we can use our first formula up here for cos. And because m and n are not equal, then we get an integral of 0 here. And once again, this is L, right? Okay, and so we get right here, this will be equal to 0. Okay, good. Okay, let's look here. Okay, if we have sine of pi theta, and we want to make this equal to sine of m pi theta over L, well then L with L equal to 1, right? So we'll get rid of that 1 there, and m also equal to 1. Okay, similarly for sine of 5 pi theta equaling sine of m pi theta by L with L equal to 1, okay, and m equal to 5, okay? Good, and so we see here that L equals 1, and so we have 1 to negative 1 here, right? Okay, So we see, okay, this works for our bounds of our integration. And we also see that these coefficients here are not equal to one another. And so therefore we can use, let's go up here. So we have two signs. Our bounds are from L to negative L. And M does not equal N. So therefore this evaluates to 0. And so this will equal to 0. Okay, good. Next we have sine squared of t dt. Okay, in this case, we could rewrite this as sine t times sine t, okay? And both of these, the coefficients are the same. And L would equal to pi, right? And that's because if we want sine of t to equal to sine of m pi t over L, then L has to be equal to pi, and m will be 1, okay? And we see right here that our bounds are appropriate, okay? And so this will equal to sine squared t dt. So we have sine times sine, but we have our m and n being the same. So let's go back up here. We see when they're the same that this evaluates out to L, right? Okay, so that's just whatever our L value would be. And so this will be pi, okay? And this is half of the period. Okay, so it evaluates to half of the period. Okay, good. We have a similar example here, cos squared pi t. So if we have cos of pi t, and we want to make that equal to cos of m pi t over L, then we would find L is going to equal to 1, and m is going to equal to 1 as well. And we see here that our L equals 1 corresponds with this one here. Okay, so we do have the proper bounds. And once again, this is a cos case where they are the same. So the coefficients are the same as before. And so we get half of the period being 2 times L. So we just get 1 here, right? So whatever L value is, it goes here. And this is the same logic as before. Okay. Rearrange my eye there. Good. Okay, and so now we have cos squared pi t dt. Okay, and so here we have our bounds going from -4 to 4. Cos squared pi t dt. Okay, and so we have a little bit of an issue here where well, let's just go through it, right? So if we were to say that cos of pi t, we want to set this equal to cos of m pi t over L. Okay, and so we want to take a look at this. So we have cos of m pi t over L, and this will be with L equals to 1 and m equals to 1, like before. But we see an issue here is that our bounds go from -4 to 4. They don't go from what we would expect to happen of going from -1 to 1. Okay, so we have to think about this. But what we can actually do is solve this. If we were to make L 4, right? If L is 4, because we need it to be here, right? That means M would be 4 as well. So if we have 4 over 4, they cancel out. Then we get pi t. Okay, and so that means we can actually use our logic up above, right? So it's just a little bit of a trick there. And so we can deal with that using our logic up here. We have cos times cos, m equals n, we get L. So this will be equal to 4. Okay, good. Okay, and this is also works because remember, a period of a function times some positive integer is also a period, right? For that function, right? So this could have a period of 2 pi, but it could also have a period of 8 pi, right? Okay, and so we get this right here. Sorry, that was wrong. We could have a period of 1, but we can multiply that by 4 and have a period of 4 as well. Okay, last time, and it's going to be right. Right? So remember, the period is 2L. So in this case, it's 2 times 4, which is 8, right? And half the period is 4. Okay? So we could have a period of 2, which we did up here. This period is right? 2 times L. 2 times L is 2, right? But it also has a period of 8, which is what we did here in order to deal with this and having the correct bounds up here. And I'll just highlight this and this and this. Okay, cool. So what we've done here is we've evaluated some of our integrals using the integrals provided on the previous page. Okay, and these will come in handy for our next bit of this chapter. Okay, finally, let's get to a Fourier series. Okay, with Taylor series, our goal is to interpret a function by an infinite polynomial. For some interval of convergence, we are able to say that a function f of x is equal to its Taylor representation, determined by a selection of coefficients in front of the powers of x. Okay, so we've seen before, we take any function, we can represent it as an infinite polynomial. We looked a lot at using that when we did a power series solution to our DEs, right? And our goal was to find the values of those coefficients, right? And so we can represent any function as a Taylor series, and that itself is an infinite polynomial, which then our problem becomes finding the values of those coefficients that appear in front of those various powers of x. Okay? The aim of a Fourier series is very similar. The difference is that Fourier series represents a function f of x by not an infinite series involving powers of x, but an infinite series involving sine and cosine functions. Okay, let's add in the x. Okay, actually, I think I'll use their full spelling. Sine and cosine functions. Since the functions making up a Fourier series are all periodic, Fourier representations may be found for periodic functions of all sorts. Okay, so the Fourier series is used when we have a function that is itself periodic, and we can thus find a representation for it in terms of sine and cosine functions. Now, consider a function f of x with period 2L and set it equal to an infinite series of trig functions. Okay, so we get f of x is equal to a naught by 2 plus the sum from m equals 1 to infinity of am, so some coefficient, times cos of m pi x over L plus bm sine of m pi x over L. Okay, so a little bit more complicated than our Taylor series, but not that much harder. We can kind of wrap our heads around this, but let's talk a bit about what's going on here. Okay, so here we have L. This is a constant, and we know that our period up here influences this L value, right? So whatever our 2 times something is, that something goes into all of these. Okay, good. And then we notice that m right here is the same value that we have inside this sum. And so that means each successive term in the sum will have a period smaller than the previous term. And when we do an example with this, you're going to see this happening in practice, okay? So each successive term in the sum will have a period smaller than the previous term, okay? And that's because m is increasing towards infinity, right? And remember that 2 pi over k, which in this case is 2 pi over m pi over L, which is equal to 2 pi over m pi times L, is our period of these functions, right? And these pi's cancel out, right? So as m increases, the period of these terms decreases, right? Because m is getting larger, and our period of the mth term is going to be 2 over m times L, okay? We assume convergence of this series for now, though it turns out that this is not an issue. Our goal is to determine the A and B coefficients that make this expression true, okay? So as with a Taylor series, once we put it into the formula, our goal is to find the values of our coefficients that describe the particular function we're dealing with, okay? Okay, so let's figure out how we're going to do that here. To do so, consider any fixed positive integer n, okay? And first multiply this equation by cos n pi x over L. We get, okay? So we're multiplying this equation right here. I'll keep both of them on the screen. We're multiplying this by cos n pi x over L. So we'll get f of x times cos of n pi x over L is equal to a naught by 2 times cos of n pi x over L, right? Plus the sum from m equals 1 to infinity of am cos m pi x over L times cos of n pi x over L plus, I'll put a squirrely bracket, a circle bracket there, plus bm, now this is sine of m pi x over L cos of n pi x over L right here, and close that bracket, okay? And all that I've done here is I've multiplied every term by cos n pi x over L, and that's where this term came from, that's where this term came from, and that's where this term came from. Of course, and that's because it distributes into this sum notation, right? That's why it pops up here and here. The rest of this is exactly from this previous line here. bm sine m pi x over L, and am cos m pi x over L, and a naught by 2. All of these are up here, respectively. Okay, good. Then integrate each side from negative L to L, okay? So we're going to have the integral from negative L to L of f of x cos of n pi x over L dx is equal to a naught by 2, sorry, the integral from negative L to L of a naught by 2 cos of n pi x over L dx, okay, plus the sum from m equals 1 to infinity of the integral from negative L to L of am cos m pi x over L times cos of n pi x over L dx plus the integral from negative L to L of sine of m pi x over L times cos of n pi x over L dx. Okay, good. Okay, so all we've done here is taken our previous line and we've integrated from negative L to L. Okay, and I just want to make sure. Yeah, okay, so we'll evaluate these in place. Okay, good. So now we want to consider what's going on here. Here we have cos, we have some constant times cos of n pi x over L. Okay, and so we want to think about this. Okay, we are integrating over an entire period. Okay, so recall the period of cos n pi x over L is 2L. Okay, and so we're integrating this right here. We're integrating over it over an entire period. We are integrating over an entire period, right? From negative L to L. And so therefore this will equal to 0. Okay, and that's because, so therefore it will equal 0 because the area above the x-axis is equal to the area below the x-axis. Okay, so our cosine function, if we integrate over an entire period, the area above is equal to the area below, right? It's centered at the x-axis. And so therefore, we're going to get an area under that curve of 0 because they're going to cancel each other out. Okay, and so this first term will be 0. Okay, good. Next, let's look at our next term. Okay, so we have some constant times cos m pi x over L, cos n pi x over L. Okay, and here we're going to have two things happen. If m does not equal n, then, right, if m does not equal n, then it equals 0. But if m equals n, then it equals to a n times L, right? Because this whole thing will equal to L. So this whole thing will be a n times L. Okay, and let's just think about this. A n is here because remember m is equal to n at this term, and all of this right here will equal to L, and that is from our formula above that we used on our previous examples. Okay, and so this whole term, only one of the terms will be non-zero, and that term will be an times L. Okay, and finally, we have sine times cos. And remember from our equations on that previous page, and if you're not remembering this, just pause the video, scroll up, then continue the video. We would see that this will be equal to 0, regardless of whether m equals n for all m values. Okay, good. And so, yeah, okay, so we'll do that on the next page. Okay, so what we did here is we used some logic and we used some of our equations from before to simplify this dramatically. And so this final term will equal to 0. Okay, So let's just continue our notes below. Evaluating these integrals is not that hard at all because of the orthogonal properties that we just discussed. The expression drastically reduces to the following, bringing us to the formula that the integral from negative L to L of f at x cos n pi x over L dx is equal to ANL. And so therefore, AN is equal to 1 over L times the integral from negative L to L of f at x cos of n pi x over L dx. Okay, good. So that means we can find all of our values AN by using this formula. We take our original function, multiply it by this cos, integrate, and then divide by L, and we get the value of N, right? And remember, L itself is half of the period of our function f of x, okay? And this will be for all, N is an element of Z, N is greater than or equal to 1. Okay, right? Our coefficients start at 1. So for all coefficients above or equal to 1. Okay? This gives us a way to figure out what our A coefficients should be. We can find a formula for Bn by instead multiplying the series by sine n pi x over L and integrating from negative L to L. The process is very similar, and we get a similar looking formula. This is for you to try. We'll have it introduced on the next page. Don't worry. Okay? Good. This leaves us one last coefficient, A naught. We can find A naught by not multiplying the series by anything and just integrating both sides between negative L to L. Since all of the basic cosine and sine functions are being integrated over entire periods, we automatically know that the functions inside the sum must give us a result of 0. Okay? So let's look at that. Integrating, we get, so the integral from negative L to L of f at x dx is equal to the integral from negative L to L of A naught by 2 dx plus the sum from m equals 1 to infinity of the integral from negative L to L of A m cos m pi x over L dx. Let me just make sure I got that right. Scroll up a couple pages. Am cos m pi x over L. Yeah. Am at cos m pi x over L plus the integral from negative L to L of Bn sine n pi x over L dx. Okay, so all we've done is integrated from negative L to L on our original function f of x, equaling to our Fourier series on the right-hand side. Okay, and so this left-hand side will stay the same, negative L to L of f of x dx is equal to, okay, so this first term, we can actually evaluate this integral. So we're going to get A naught by 2x evaluated from negative L to L plus, okay, well, here we have some constant times cos, but we're going over its entire period. So this will be equal to 0. And once again for sine, but we're integrating over its entire period. So this will be equal to 0. And this is precisely what this, let's do a different color. Control Z, sure. Equals 0. Functions inside the sum give us a result of 0. That is exactly what this previous paragraph was talking about, saying that this all simplifies, so we get plus 0. Okay? And so that means we have the integral from negative L to L of f at x dx And this equals to a naught by 2 top L minus bottom negative L. And so this equals a naught by 2 times 2, times 2L. These 2's will cancel out. And so we get the integral from negative L to L of f of x dx is equal to a naught times L. And so therefore, a naught is equal to 1 over L times the integral from negative L to L of f of x dx. Okay? Okay, so that means we can also find our coefficient a naught using this third formula that we've now derived. Okay? So in the end, we obtain these three useful formulas. an equals 1 over L from the integral of negative L to L of f of x cos n pi x over L. Bn right here, and a naught right here. Okay, I'm not going to read all of those out, but we get these three formulas, and we can use these formulas to solve for our various coefficients. Okay, good. So then we have an example. Find the Fourier series for f of x is equal to 3 from negative 2, from x equals negative 2 to 0, and 1 from 0 to 2. Okay, with periodicity given by f of x equals f of x plus 4. Okay, so this is saying our period is equal to 4, okay, which is equal to 2L. And so therefore L equals 2. Okay, but we'll come back to that in a moment. Okay, good. First, let's draw what this looks like. Okay, so I am going to use negative 2, negative 4, negative 6, 2, 4, 6, and let's do 1, 2, 3. Okay, so from negative 2 to 0, we are going to have a height of 3. Negative 2 is inclusive. 0 is not. Okay, height of 3. And then from 0 to 2, we're going to have a height of 1. 0 is inclusive, and 2 is not. Okay, good. But we also know that periodicity is 4, right? Our period is 4. So this is repeating. So that means here, once again, we have this height. Okay, and then here we have this height. And then here we have, oh, sorry, wrong way. Here we have this height. And then here we have this height. Okay, good. And all of this right here comes from the fact that we have a periodicity, this property right here, where it is repeating outside of the bounds from negative 2 to 2. Okay, good. So we have this function right here. Okay, now let L equal to 2, since the period is 4. Then we must find the coefficients an for n is 0, 1, 2, etc. And bn for n is 1, 2, etc. Let's use our new formulas and some integration muscle. Okay, so first we want to find a naught. Okay, so a naught using our formula is equal to 1 over L times the integral from negative L to L of f of x times nothing dx, right? We don't multiply by anything for this one. Okay, we can plug in our values. So we get 1 over 2, the integral from negative 2 to 2 of f of x dx. Now, f of x is a piecewise function, so where there's a discontinuity, we have to break it up. And so this would become 1 over 2 times the integral from -2 to 0. The height is 3 dx plus the integral from 0 to 2, and the height is 1 dx. Okay? Good. So all we've done here is we broke our function that's piecewise up into its two pieces because it has a different height at those various pieces. Okay? And so we get 1 over 2 times, well, this will be 3x evaluated from -2 to 0 plus x evaluated from 0 to 2. Okay? This will be 1 over 2 times, okay, 3 times top 0 minus -2, okay, plus 2 minus 0. Okay, so this will be 1 over 2. This will be 3 times 2 plus 2. Okay, we'll continue up here. Is equal to, and remember this is a naught, is equal to 1 over 2 times 8, which is 4. Okay, which is 4. Okay, note, we want to remember that, recall, the first term in the Fourier series is a naught by 2. So our first term will be 4 by 2, which equals to 2. And I just recall there being a second note, so I'm just going to check my notes beforehand and make sure I don't miss anything here. Okay. Yes. Okay, that was missing something. Okay, cool. Let's go back to where we were. Okay. So that note and this value will always be the average value of the function. Okay, so whatever value is our first term in our Fourier series, in this case it's 2, so I'm not talking about a naught, I'm talking about a naught by 2. That will always be the average height of our function, right? And we see that being the case. Let's look up here. So I'm telling you the average value of this function will be 2. Let's look up here. Well, half the time the height is 3, right? And the other half the time the height is 1. So on average, the height will be 2, right? Okay, so that first term will always be the average height of the function. Okay, good. Okay, now we're ready to keep on trucking. Okay, let's now look at an. So now we want to find our an for n is greater than or equal to 1, right? Because we found a naught. Okay, an will be equal to 1 over L times the integral from -L to L of f at x. And I believe it is cos, but I'm just going to go double check. Cos n pi x L over L dx. Cos n pi x over L dx. Okay, good. Let's plug in our values. So we get 1 over 2 times the integral from -2 to 2 f of x cos n pi x over 2 dx. Okay, and make sure we also plug that 2 for L in over here. Okay, good. And so now what we're going to do is we're going to do the same thing, and we're going to break this apart based on our various heights. So we have 1 over 2 square bracket And our first piece will be the integral from -2 to 0 of 3 cos n pi x over 2 dx plus the integral from 0 to 2 of cos n pi x over L dx and square bracket here. Okay, good. So then I have equals 2, 1 over 2. Okay, so we're going to do some chain rule in reverse here. So if we have 3 times cos n pi x over 2, the integral of this will be 3 times the inverse of this coefficient. So 2 over n pi sine of n pi x over 2, evaluated from -2 to 0. Okay, good. If you need to pause here, do that off to the side. If this is not clear to you, it's important that it's clear to you. But if you can see how if we were to take the, if we were to take the derivative of this, we would get back to 3 cos n pi x over 2, and that's because of chain rule in reverse. Okay, plus, okay, we'll do the same thing here, n pi over, I meant to have a 2 here. Okay, so it'll be 2 over n pi sine of n pi x over 2, evaluated from 0 to 2, square bracket here. Okay. And what I'm actually going to do is I'm just going to bring through this half, and so that'll get rid of these 2's. Okay. Perfect. So now we have 3 over n pi, and I'm going to actually evaluate these sine functions for these intervals. So I'm plugging in 0 top. So we have sine of 0 minus, okay, sine of, well, we have n pi -2 over 2. So it'll be, well, I'll write it out. N pi -2 over 2. Okay, and so these 2's cancel out. So we have negative n pi inside this sign. Square bracket here. Okay, we'll come back to that in a moment. Let's do our second valuation here. So we have plus 1 over n pi times sine of n pi 2 over 2. So these 2's cancel out. Okay, minus sine of 0. Okay, let's do our easy simplification first. Sine of 0 is 0. Okay, so that goes to 0. But then let's look at this one. We have sine of some positive integer times pi. And let's just confirm that n is a positive integer. I'm pretty sure it is, though, when we multiplied through this. We're going way far back. It's okay. Positive integer n. Good. Okay. So n is a positive integer in this multiplication. Let's get back to where we were. Okay. So we have n times pi. So some multiple of pi. Okay. And every time sine traverses a pi, starting from 0, we're going to hit 0, 0, 0, 0, 0, right? Infinitely. It's always 0 for whatever n. So this is also 0, and this is also 0, because this would just be negative n times pi, which will also be 0, okay? And so in fact, this whole term simplifies to 0 plus 0, which is 0, okay? So an equals 0 for all n greater than or equal to 1. Okay? So, note, all cosine terms will have a coefficient of 0. Okay? All cosine terms will have a coefficient of 0. But this isn't surprising because our function f of x is odd, and that means odd means if we have f of x, that equals to negative f of negative x. Yeah, I think it's normally expressed as f. Yeah, okay. Normally that is technically true, but f of negative x equals negative f of x. Shifted up. Okay, so let me go through that because I had multiple ideas there. So this isn't surprising because our function f of x is an odd function that's shifted up. Okay, and remove that period to have some proper English. And cosine of x is an even function. And recall that an even function means f of negative x equals f of x. Okay, so our cosine is an even function, but we're trying to represent an odd function, right? So it makes sense that we're not going to see any cosines appearing inside inside our terms, okay? Or inside our Fourier series, okay? We'll put a bracket around this. Okay, good. Okay, let's do our final integral to find our values of Bn. And this is equal to 1 over L times the integral from negative L to L of f at x sine of n pi x over L dx. Okay? And so we will then plug in our value for L. We have 1 over 2 from negative 2 to 2 of f at x sine n pi x over 2 dx. As before, we're going to break this up because f of x is a piecewise function. We're going to break this up into the integral from negative 2 to 0 of 3 sine n pi x over 2 dx plus the integral from 0 to 2 of sine n pi x over 2 dx. Okay, perfect. So we've broken this up into two pieces. And then we want to investigate this more. So we have 1 over 2. Okay, good. And then we want to look here. So we have the integral of 3 sine n pi x over 2 dx. This will be similar to our previous example here, or previous coefficient that we were solving for. And so we'll just go ahead and do that. This will be 3 times 2 over n pi cos. This will be negative, right? Cos of n pi x over 2, evaluated from negative 2 to 0. Okay, so the difference is we bring a negative in because we're taking the integral of sine instead of cos, and the rest of it remains the same. And then this will be minus, okay? This will be 2 over n pi cos of n pi x by 2, evaluated from 0 to 2, close bracket here. As before, I'm going to carry this half through and eliminate these. Okay, and so then I would have negative 3 over n pi times, let's evaluate this. So we're going to have cos of n pi x over 2. We're plugging in top first, so we have cos of 0 minus cos of, we plug in a negative 2 here. I am going to skip one step. We'll have negative n pi. Right? So if we plug in negative 2 for x, the 2's cancel out, but the negative sticks around. Same thing that happened before, except we're doing it in cos. Square bracket here. Good. Minus 1 over n pi, square bracket, cos of n pi, right? The 2's cancel out when we plug it in, minus cos of 0. Okay. Now, let's simplify this a little bit. Cos of 0, we know will be 1. Okay? And cos of nx and cos of negative nx, well, we're going to have to do a little bit of more work here, but that's fine. But the first step of simplifying this a bit is I am going to replace cos of n pi. This is the same as cos of n pi, right? Because cos is an even function. So once we have up here, cos is an even function. And so let's highlight this. That's how I did this replacement right here. Okay, good. Okay, so then we get negative 3 over n pi. This will be 1 minus cos of n pi. Okay, minus 1 over n pi. And then this is cos of n pi minus 1. Okay, so the two terms are just flipped, right? Or multiplied by negative 1. Okay, so what we can do is we can factor out a negative 1 of the second brackets, and we'll get this. So we would get negative 3 over n pi, 1 minus cos of n pi. Okay, plus, we're factoring out a negative, 1 over n pi times 1 minus cos of n pi. Right there, right? Okay, and all in all, this equals to negative 2 over n pi times 1 minus cos of n pi. Okay, good. So we do have a formula, but we can make this a little bit simpler. Let's recall that what's going on with our cos. So cos of n pi will equal to, well, we have two values, right? If n is even, so 0, 2, 4, if n is even, then this will have a height of 1. Right? So if we plug in cos of 2 pi, it goes woo, woo, back to 1. 4 pi, woo, woo, back to 1, right? Negative 2 pi, woo, woo, back to 1. Okay, good. Now, if we have an odd number, remember n has to be an integer. N is an element of z, and n is greater than or equal to 1. Okay, right? If we have an odd number, then we only go pi. So we start at the top, we go 1 pi, woo, and then 2 pi will be back up. So we're at negative 1. So this will be negative 1 when n is odd. Okay, good. Okay, so that means we can actually use that to make a piecewise function for this. And so this will be equal to, well, if n is even, right? If n is even, then we plug in 1 here. We get 1 minus 1. That's 0, right? So this is 0. If n is even, it's 0. But if n is odd, then this will be negative 1. So we have 1 minus negative 1. So that becomes 2, right? So we get negative 4 over n pi for n is odd. Okay, good. And so this is equal to Bn for all n is greater than or equal to 1. Okay? And so we have this here. Okay, we're so close. Let's bring it all together now. Okay? Therefore, the Fourier series for this function is f of x is approximately equal to, okay? Remember, a naught by 2. Let me write out the full formula first here. So we have a naught by 2 plus the sum from m equals 1 to infinity of am times, what was it? Cos of m pi x by L? No. Yeah, it has to be L. It's L dx plus bm sine of m pi x by L here, and brackets here to say they're both in the sum. Okay, so we have here, and now we're sort of plugging in our things. Okay, so we know a naught by 2, we calculated up here. That is going to be 2 because we have a naught by 2, right? A naught was 4. So this becomes 2, okay, plus, okay, and now every single an term is 0, right? So that means there's no coses in the rest of it, but there's going to be sines, okay? So let's think about our sines. Whenever n is odd, we get this, negative 4 over n. So let's do our first term. So we're going to get minus 4 over n equals 1. So we're going to get pi, negative 4 over pi, sine of pi x by 2, right? Because L is 2. Pi x by 2. Okay? Good. And then we're going to have our next an is even, which is going to be 0. So for n equals 2, we don't have one, right? But we will for n equals 3. So let me just actually label these as we go. So this corresponds to that term. This is our n equals 1 term. Okay? For n equals 1, we get this. Good. Then for n equals 2, there's no terms. Right? Because this is 0 and every single a coefficient is 0. Right? But then for n equals 3, we get minus 4 over 3 pi sine of 3 pi x by 2. Good. And this is our n equals 3 term. Okay, for n equals 4, there's no terms. Same as before. Then minus 4 over 5 pi sine of 5 pi x over 2. Okay, plus dot, dot, dot. This will continue forever. We're doing these 3 terms. Okay, good. Okay, and so we get this equation right here. And so this is our Fourier series for our function f of x using sine and cosine. Okay, good. Okay, so we've seen how we can find these coefficients. Okay, and I just want to, for some reason, it's seeming like this is a little bit wrong. So I'm just going to double check my practice work. Negative 4 over 3 sine 3 over 2. Nope, that's correct. I believe. Negative 4 over 3 sine 3 over 2. Yep. Okay, perfect. Good. Okay, and let me label this last one. This is our n equals 5 term. Good. Okay, good. And now remember how before I said how every time we add another term, the period's getting smaller? You're going to see that here. Okay, good. In the following figures, we can easily see how taking more and more terms in the series causes the resulting functions to approach the shape of f of x. Good. So in each of these figures, we're adding one additional term. So this is f of x equals 2, right? Okay, that looks nothing like the function, right? But we're starting there, but we do notice that this is our average value. Okay, good. And now we're going to add our next term here. So we have f of x is equal to 2 minus 4 over pi of sine pi x by 2. Okay? And so we see, okay, once we do that, okay, well, we're hoping that this is going to be around 3 here and 1 here. Okay, so it's starting to approach that. Good. And the period here is 2 pi, right? Or no, it's just pi. No, it's just 2. It's 4. Oh my gosh. 2 pi. Let's just find it. 2 pi by k, which is pi by 2, which is 4. Yeah, good. Our period here is 4. Good. Now let's add one more term. So f of x is equal to 2 minus 4 over pi sine of pi x by 2 minus 4 over 3 pi sine of 3 pi x by 2. Okay, good. And so we see here, okay, now it's starting to fluctuate around our heights that we're looking for. Because remember, it should be like here, and then here, and here, and this is looking there. Okay, so it's starting to approach that. But you also notice the curves that we're seeing are within the previous curves, right? So our period of these functions are decreasing, right? Good. Each term is decreasing, how it's changing it. Okay, good. The period of this overall function is still 4, but the period of this term is not, right? This term has a smaller period, and so we're seeing smaller fluctuations happening within our curve. Okay, and this is now with 4 terms, and it's exactly what we had up here. And if we continued this, we can see to infinity, we're going to eventually have our function here approximated using a Fourier series. Okay, awesome. Let's do one final example. It's a bit trivial, but find the Fourier series for this function. Okay, this function is already made of sine and coses, right? And our Fourier series is meant to give us a function that is comprised of sines and coses. Okay, this one's already sines and coses. Okay, so it's a little bit trivial, but you'll see what happens. Let's just think about this. The period of sine x is what? I'm thinking I'm in a class. The period is 2 pi. Okay, this period is equal to 2 pi by 4 by k, which is equal to pi by 2. And this period is 2 pi by 11, which is 2 pi by 11. Okay, good. So we have to think about our overall function, right? All of these have different periods, but what period is going to be shared by all of them, right? Because each of these individual components has different periods, right? Well, if we multiply this by 4, then we get 2 pi, right? And so remember, any positive integer times a period is itself a period, right? So that means this sine function also has a period of 2 pi. Perfect. And if we multiply this by 11, then we get 2 pi again. Okay, good. So all 3 of these individual functions has a period of 2 pi. Good. And so the period of f of x is equal to 2 pi. And so therefore, L equals pi. Okay? Therefore, L equals pi. Okay? And now we can use that to determine our various functions, right? And let's rewrite our equation here. We have f of x is equal to a naught by 2 plus the sum from m equals 1 to infinity of am cos m pi x over L plus bm sine of m pi x over L and brackets here. Okay, good. We have this. Well, there's no constant term in our f of x there, right? So a naught's going to be 0, right? In fact, a lot of these are going to be 0. But we need to deal with these sine, and cos. So 5 sine of x. Well, in order to get a 5 sine of x from this term, we're going to meet, that means that bm has to, or that means that this coefficient has to equal 5, but it has to be the term that is going to cause this to be 1. So that means b1, right, is equal to 5, right? Because we want our coefficient to be 5, right? And we want inside our sign to just be x, right? But L is pi. So let me actually replace this and simplify this quite a bit. L is pi, L is pi. Eliminations, eliminations. Okay, good. And so that means in order for us to have a term in order for us to have the term 5 sine x, that means we need a coefficient of 5, and we need what's inside sine to just be x. So that means m has to be 1. So b1 equals 5, right? b1 equals 5. 1 and 5. Okay, and that will give us 5 sine x. 4, negative 1 over 4 sine of 4x. That means, well, we need a coefficient of negative 1/4. So that means one of the coefficients has to be equal to negative 1/4. But the coefficient that is negative 1/4 has to be b4, because this m value goes into here. And so we get 4 times x. 4 times x. So I'll highlight here. It's a bit clearer here. The fourth coefficient of b has to be equal to negative 1/4. Okay? And our final term is 4/23 cos 11x. We're going to have a, right? Because that's what's in front of cos. So a 11 has to equal to 23. And that is the same logic here. A 11 in order to get that inside part, and 23 in order to get that outside part, and all other AIs and BIs will be 0. Okay? Awesome. This is analogous to the case of trying to find the Taylor series for a function that is a polynomial in the first place, right? You don't need an infinite series of powers of x if your function is made of just powers of x to begin with, right? The Fourier series for sines and cosines isn't going to be an infinite combination of sines and cosines. It's going to be literally those sines and cosines, right? And so this was a bit of like a, let's just nail that home with this example, okay? Awesome. I hope you enjoyed this video. I hope you enjoyed the class, and I wish you all the best in this upcoming semester and the rest of your futures. Thank you very much once again for the great opportunity to teach you. It's been amazing this last semester. I definitely miss you guys, miss teaching, and I miss yelling at the start of the class. And I'll see you guys around campus until I'm gone, and hope to see you again in my future. Thank you, and have a great day, guys.